We're about to look at the concept of estimable functions. As it turns out, not everything can be estimated in all linear models. And before we dive into the theory, let's just look at one or two examples. Here's the usual one-way layout. Here we write the response as an overall mean plus a group effect. Here you cannot distinguish the mean from all the group effects. You can add a constant to the mean and subtract the same constant from all the group effects, and you'll get the same sum, so it's not a fully identifiable model. Now, this is easy, but there are many cases where this is a bit more difficult. For example, in the case of multiple regression lines, one coefficient for each group as in equation 5, you may sometimes want to test the effect of these groups, and a typical model would be to fit a single regression line first and then add a component for each group for testing purposes. And the tests we've looked at will allow us to do this. But obviously, the betas cannot all be estimated individually. Now, for the testing purposes, it don't need to be tested, it don't need to be estimated individually, but we may sometimes want to be more explicit. So the point is that there are several cases where it's not at all clear at the outset what can be estimated, and we want to set up a general framework for this. This is done through the use of estimable functions, an estimable function is simply a function which can be estimated. And to put some restrictions on this, when we say estimable functions in this context, we mean a linear combination of the parameters. And the estimate is a linear combination of the data. So if there exists a linear combination of the data, so that the expected value of this linear combination is always equal to C prime beta, no matter what the assumption is on beta, then we call it estimable. And of course, A prime Y is the estimate. We want to see when is this estimable, when does this hold, and how do we estimate it. And as it turns out, there are certain criteria which tell us when this is estimable. And the overall theorem is that a parametric function is estimable if and only if we can write the vector that describes the linear combination. We can write it as a vector A transpose times the X matrix itself. In other words, the vector C is a linear combination of the rows of the X matrix. And this theorem we can prove easily. It's simply a question of the expected value. This is the expected value of A prime Y. It has to be equal to C prime beta for all betas, and from that the result follows. Now there's a theorem which tells us that that every single estimable function has a unique and unbiased linear estimate, which has the minimum variance in the class of all unbiased linear estimators. And if you take any estimator whatsoever of the beta, remember it may not be unique, but if you take any one of them and use that in the linear combination, then that will give you the same estimator no matter which one you originally picked. So the unique unbiased linear estimators can be derived from any of the least squares estimators to begin with. So that's a unique property of the estimable functions. It doesn't matter which least squares estimator you stick in. The proof of this comes in two steps. The first is that if you have an estimable function, then there's a unique estimator with the solution, the coefficient vector in V. Now remember, V was the span of the X matrix. And if we have any other estimator which is unbiased, then this unique A is the projection of A0 onto B. And we remember that the projections are unique. And then the Gauss-Markov itself is the theorem we stated at the beginning. And we're going to take another short video where we prove these two things. But here it's enough to note what this says is that anything we can estimate is estimable through the X matrix. And you remember that our error estimates, they were derived on the residuals which are orthogonal to the columns of the X matrix. This thing here is a function of the X matrix. So anything estimable comes from the X matrix. Anything used for the error comes orthogonally to the X matrix.